Lesson 10.5, Taylor and Maclaurin series. In the last section, we created power series for functions using geometric series, along with substitution, long division, and term-by-term differentiation or integration. Let's develop a procedure in general for writing the power series for a given function that will have derivatives of all orders. We will find that every convergent power series must take on the form of this right here. Okay, so that form is what so if f is represented by a power series, f of x equals the summation of a sub n times x minus c to the n for all x in an open interval containing c, then a sub n equals the nth derivative at c divided by n factorial, and f of x equals f of c plus f prime of c times x minus c plus f double prime of c divided by 2 factorial times x minus c to the second plus dot 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 plus the nth derivative at c over n factorial times x minus c to the n. That would be your nth term. Note, be sure you understand that this theorem says if a power series converges to f of x, the series must be a Taylor series. It does not say that every series formed with the Taylor coefficients, a sub n equals the nth derivative of c over n factorial, will converge to f of x. The formal definition of Taylor series is stated below. So we have if a function f has derivatives of all order at x equals c, then the series summation from n equals 0 to infinity, the nth derivative of c divided by n factorial times x minus c to the n, which is equivalent to what we just said above, is called the Taylor series for f of x at c. Also, if c equals 0, then the series is the Maclaurin series for f, which we have been saying that for the last couple of lessons. Example number 1, it says find a Maclaurin series for f of x and give the first 4 non-zero terms and the general term. So we do not want to just take a bunch of derivatives here because that's going to get really ugly. I mean, we could, but there's a faster way. That's why we're calling it shortcuts. Okay, so I'm going to show you the shortcut way, and it's going to be a lot better than having to take all those derivatives. First, we're going to find the Maclaurin series for e to the x, for f of x, for f of x equals e to the x. Now, that's something that I kind of wanted you to remember, but if you don't, I mean, try to think about it that, you know, first you have e to the 0, then you have e to the 0 times x divided by 1 factorial, then you have e to the 0 times x squared divided by 2 factorial. You know, so it's pretty easy to produce this one, and you'll see that this is equivalent to summation n equals 0 to infinity x to the n over n factorial. And for those of you taking the AP exam, you need to have this on your paper right next to because they allow you to have that. So there are some in your book, and I will go through that with you, but there are one Maclaurin series that they want you to have memorized in your book. But you don't have to have them memorized because you're able to use that piece of paper this time. So in prior years, all my AP people had to memorize these. And so you guys have an advantage because you're able to have a piece of paper there. But now we can just use substitution here. We know that this is now equivalent to summation n equals 0 to infinity of negative 2x to the n over n factorial. So you can just put that negative 2x in for x. And now we're wanting to simplify this because we want, you know, to see what it is. So we're going to take that negative 1 to the n out, and then we've got a 2 to the n, and we've got an x to the n. Okay, that's how you would want to break that apart. And then go ahead and look at what you get. So if you put 0 in, you should get 1. If you put 1 in, you should get negative 2x. if you put 2 in, you should get positive 4x squared over 2 factorial. If you put 3 in, you should get negative 8x to the third over 3 factorial. And, you know, you could just keep going. But there's your Maclaurin series. There's your first 4 non-zero terms. And our general term was this right here, okay? Use your answer to find a Maclaurin series for f prime of x. So once you've got your series, we're going to take the derivative, right? And you can just take the derivative term by term. That's what we call term by term differentiation. So the derivative of 1 is 0. The derivative of negative 2x is negative 2. The derivative of 4x squared over 2 factorial, I'd bring the 2 down times the 4, reduce x to the 1, and you still have 2 factorial there. And then the derivative here, I'd bring the 3 down times the negative 8 is negative 24. I'd reduce my x to the second, and then you still have your 3 factorial on the bottom. And so there's your derivative, and when you want to take the derivative of, we're actually taking the derivative of this guy right here. So plus, and then, you know, your negative 1 doesn't have an x in it. So it just stays the same. 2 to the n stays the same. The only thing and so does the n factorial. The only thing you're taking the derivative of is this x to the n. So this would be n times x to the n minus 1. And that's your answer to part B. So that wasn't too bad. Example number 2, evaluate the indefinite integral as a power series and find the radius of convergence. So for this one, we have to think about what do we have here? And what do we know that is similar? So what I did is I started to recall, and I'm scared that this one's too fat, but we're going to try and use it because I like to use the red, that our 1 over 1 minus x Maclaurin is summation from n equals 0 to infinity x to the n, okay? And that's one of them that they want you to memorize, okay? And so the reason why we want to think about this is because this looks similar to 1 over 1 minus x, okay? All we would have to do is think about it as if we took our factored the t out, right? Because there's a t in the numerator there. And this is 1 over 1 minus t cubed. We could say that this is t times the summation from n equals 0 to infinity. And instead of x to the n, it's going to be t to the third to the n. So do you see how we're using that main thing that you're going to keep on your piece of paper there, just in case you have one of these on your free response, and you're going to say, oh, I can use that to get my t, my t over, and I'm going to change colors here just because that one's too fat, darn it, and I hope this is okay, but so I'm going to bring that t inside, and this is going to end up t to the 3n plus 1. Okay, so that was a 3 and that was an n. So I multiplied that, and then when I brought the t in, I had another t, so I added a plus 1 there. So now I know that I can actually integrate my summation. Because those are equivalent to one another. So if I'm going to integrate my summation, think about what your summation is going to be. It's going to be like, t, right? Because we're gonna kind of multiply these out. That was when n equals 0. When n equals 1, I've got t to the 4th. When n equals 2, I've got t to the 7th. When n equals 3, I've got t to the 10th. N equals 4, I got t to the 13th. And, just like that. So this is what we're going to be integrating. So, of course, we can integrate that. T squared over 2 plus t to the 5th over 5 plus t to the 8th over 8 plus t to the 11th over 11 plus t to the 14th over 14 plus ... And then let's go ahead and put that last one on, because if I took the integral of t to the 3n plus 1, this is going to be t to the 3n plus 2 divided by 3n plus 2 plus some constant. When you're integrating and you have an indefinite integral, and they reminded you that it was an indefinite integral right there, and you have that, you got to put that plus c on there. So now what we just decided here was that the integral of t over 1 minus t cubed dt is equivalent to c plus summation from n equals 0 to infinity to the, sorry, I hit something, 3n plus 2 over 3n plus 2, okay? That's what we have just decided that this is equivalent to. So now, that was the first thing that they asked you for, right? If it's an indefinite integral, you're going to have a plus c. So now, we're going to, by the ratio test, we're going to figure out what the radius of convergence is, because that's the second thing they asked for. So we're going to say the limit as n goes to infinity of the absolute value, and we're looking at our n plus 1. And remember, when I take 3 times n plus 1 plus 2, I'm going to have 3n plus 3 plus 2. I'm going to have 3n plus 5. And so this is t to the 3n plus 5 over 3n plus 5. That's my n plus first, and then the reciprocal of my nth. And now I want to write this so some things will cancel. So I think about this and I think, well, I want it to cancel with my t to the 3n plus 2. So really, I've got 3 more of these here. And I can't really do anything with the 3n plus 5 and the 3n plus 2. But I was able to write this so that I can see that this and this cancel. And so this is going to give me t to the 3rd times 3n plus 2 over 3n plus 5. And remember, the limit only involves the n's. And so you can see 3n over 3n goes to 1. So this is, just basically t to the 3rd times 1. So this is going to be t to the 3rd. Forgot the absolute value there. So absolute value of t to the 3rd. And so now you're going to say, okay, so that means for this to converge, I'm going to say converges when, because I'm kind of coming up here, right, after that, and it converges when, and that is not a negative, it kind of looks like it, but the way I wrote my, okay, absolute value of t cubed is less than 1, t cubed between -1 and +1, if you took the cube root, you'd get -1 and +1. Okay, so you don't really need to check your endpoints here because they're not asking us for an interval. They're only asking us for the radius of convergence. And from this, I can see that my radius of convergence is 1. Okay, so I can just stop there. All right,